So my second derivative test is looking like I said at the concavity. So the second derivative states this: if you end up with the first derivative is equal to 0, and the value of the second derivative is greater than 0. Remember, any time that that second derivative is greater than 0, we know that we're dealing with concave up at that particular x value. So if you're dealing with a concave up, then notice on your graph, you're going to have a relative minimum at that particular x value. If you have a critical number and the first derivative is equal to 0, but the second derivative is less than 0, remember what that means. You know that the graph is concave down at that particular point. So if you're concave down, then the f is going to have a relative maximum at that particular x value. So I always, again, refresh it in my mind. What does it mean when that second derivative is greater than 0 or less than 0? Draw your u's. Because students oftentimes get confused. They want to say, oh, if I'm concave up, they think of up, it's got to be a relative max. And that's a false statement. But you know what concave up and concave down looks like. So it's always helpful to draw those u's, I think. Now, it is possible that the value of the first and second derivative is equal to 0. The test is inconclusive. Which means, it doesn't mean that there is no relative extrema there. It just means you can't tell by the second derivative test. All right, so you may have a relative max, you may have a relative min, or you may have neither. It's just you can't tell from the second derivative test. Typically, they are very specific. They will tell you that you must use the second derivative test in order to find the relative extrema. Or they are very tricky in terms, if they want you to use the second derivative, they're only going to give you enough information. You are forced to use that second derivative test. So find the relative extrema using the second derivative test. So first of all, obviously, to use the second derivative test, you have to find the second derivative. So I have to find the first derivative. So f prime of x. What is the derivative sine of 2x?
Cosine of 2x.
Cosine of 2x, exactly. We had a debate yesterday because everybody wanted to say, well, it's 2 sine x cosine x. Well, I agree 100% with that statement. It's the double angle formula, but it's not the derivative. And it's much easier to find the derivative of sine of 2x than it is 2 sine x cosine x, isn't it? Because you don't want to have to use your product rule. So this is going to be 2 cosine of 2x using your chain rule. So now, before you can get to the second derivative test, you have to actually find where the first derivative is equal to 0, find the critical numbers. So I have to take my first derivative and set it equal to 0. Now remember, you're only solving this trig equation from 0 to pi. How do I solve this trig equation? What's the first step, first of all, going back to your trig days? Well, can you divide both sides by 2 first? Yes. So 0 is equal to cosine of 2x. Oh boy, now I got to remember trig equations. Do you remember how you handle solving trig equations when you have an operation inside? Yeah, Ethan?
You use cosine squared theta minus, or squared x minus sine squared x, and then move one on the other side, so you're equal to something.
You could. Or, there's another way. Yeah, Ethan. I mean, not Ethan, Owen.
Cosine of 0 is 2x.
You're on the right track. Yep, we're getting there. Yeah. Mark.
Oh, you could put it's like 2x. You just put theta and then.
Yeah, so let theta be equal to 2x and do that general solution business. Kind of remember that? So you rewrite this as 0 is equal to cosine of theta. So find, first of all, where is cosine equal to 0 from the unit circle? So cosine's equal to 0 where?
Pi over 2 and 3 pi over 2. So just, yeah.
Now remember, that's where theta is. Remember, this is where now you have to bring in the 2x. So now I'm going to take 2x and set it equal to pi over 2. And if you remember, you have to write that general solution of 2 pi k. Why did I write a 2 pi there? Do you remember what the periodic property is for sine and cosine? Your periodic property for sine and cosine is 2 pi. What's your period for tangent and cotangent? Pi. Exactly. So if this was a tangent or cotangent equation you had to solve, again, this would just be a pi k. And then now how would you solve for x? What are you going to do to both sides of the equation? We're simply going to divide both sides by 2. So pi over 4 plus pi k. Anytime you have an operation happening on the angle you're trying to solve for, you've got to set up that general solution. So now remember, what you did back in your pre-calc days is starting with 0, you started plugging values in for k. 0, 1, 2, 3, 4, until you got out of the range where you were looking for your solutions. So if I plug in 0 for k, pi over 4 plus pi times 0 is just going to give me pi over 4. If I plug in 1 for k, pi over 4 plus pi, is that going to give me an angle larger than pi?
Yes.
Yeah, so my only angle that's going to fall between 0 and pi is going to be at pi over 4. But now remember, back a few minutes ago when I solved for theta, you told me there were 2 values where cosine was equal to 0. So you have to consider both of those particular angles. So I have to do it again. I have to take my 2x, set it equal to 3 pi over 2 plus 2 pi k. Divide by 2, so x is going to be equal to 3 pi over 4 plus pi k. So what's the only angle that's going to fall between 0 and pi here? 3 pi over 4. So that's where the value of the first derivative is equal to 0. If you are doing the first derivative test, this is where you could set up your number line. You would figure out if it was going to be positive or negative, figure out increasing or decreasing. But the directions specifically say to use the second derivative test. So then I need to now find the second derivative. So what is the derivative of 2 cosine 2x? Negative 4 sine of 2x. So now I need to figure out what's happening at these 2 critical numbers in terms of the concavity. So I'm going to plug pi over 4 into my second derivative. So I have negative 4 times the sine of 2 times pi over 4. So I want to know in terms of concavity what's happening at pi over 4. What is 2 times pi over 4? Pi over 2. So the big question is, what's the sine of pi over 2? 1. And 1 times negative 4 is negative 4. So I know negative 4 is less than 0. So now, in terms of pi over 4, what's happening with my concavity at pi over 4? Am I concave up or concave down? Down. I'm concave down. So what does that tell me at pi over 4? Am I dealing with a relative max or am I dealing with a relative min? Max. So now with your second derivative test, guys, you've got to state 2 conditions. First of all, you must state that f prime of pi over 4 is equal to 0. You must state that. And the second derivative of pi over 4 is less than 0. So there's 2 conditions you have to state. You have to state that the first derivative was equal to 0 at that point, and you must state whether or not it was greater than 0 and less than 0. So since the second derivative is less than 0, we know that we have a relative max at x equals pi over 4. All right, so any questions on knowing that we have a relative max at x equals pi over 4? Okay. You guys go ahead and tell me what's happening at 3 pi over 4. The second derivative. All right, so any questions on that one? So any questions on using the second derivative? Obviously, guys, it's easier if you have the first derivative. Just if you're not told specifically, just go ahead and use that first derivative and you can tell relative max and mins. But either they're going to specifically tell you to use the second derivative test, or you only have enough information to use the second derivative test. All right, so now here's an example. Use the given derivative. Now look how nice they are. One of the most common errors students make is when you see that word, you want to find relative max, relative min, or neither. You're not paying attention to what function they're giving you. I can't tell you how many times on tests and quizzes I've seen students waste so much time because they don't recognize that this is the first derivative. They go through that ugly process of finding the second derivative. They're not specifically telling you to use the second derivative test, are they? No. So now, if they give you the first derivative and you just want to know relative extrema, they've given you half the battle. Remember, where are the relative extrema going to occur? It's going to occur where f prime of x is equal to 0 or where f prime of x is undefined. That's where your relative extrema can occur if you have that sharp point. So first of all, I've already done the derivative. They've already done all that ugly work for you. How do you figure out where this derivative is equal to 0? You're going to set what equal to 0? Numerator. So x squared minus 7 is equal to 0. I'm going to add 7 to both sides, so x squared is equal to 7. What's x going to be equal to? X will be equal to? Plus or, oh, very good. You did not make that ugly algebra fatal error. Forgetting that negative. Now, where is this going to be undefined? It's going to be undefined where?
When at the bottom.
When the denominator is equal to 0. Yep. So I know I'm going to cube both sides, so x squared plus 4 is equal to 0. What kind of answers do you get here? Do I get real? Imaginary. I'm sorry to break your hearts. We're never going to deal with imaginary numbers in here. I know. It's so sad. I had one student a couple years ago that absolutely loved imaginary numbers, and he so desperately wanted to do imaginary numbers in here. I'm sorry to break your hearts if you are that attached to imaginary numbers, but there is no real number where we're going to have the derivative undefined. All right? So again, let's just go ahead and set up the number line. So I've got negative square root 7, and I've got positive square root 7. So again, the denominator. Is this denominator ever possible to be negative? Will this denominator ever be negative when I start plugging numbers into the derivative? No. So really I just need to figure out what's happening in the numerator. So what is a pretty number? I say pretty. Let's not deal with decimals or radicals. What is a pretty number less than negative square root 7? Negative 3. Because remember, square root of 7 falls between square root of 4, which is 2, and square root of 9, which is 3. So I know I can plug in negative 3. When I plug negative 3 into the first derivative, what's happening in that numerator? Is it positive or negative? Positive. So I know that I'm going to be increasing less than negative square root 7. Plug in a number between negative square root 7 and positive square root 7, which is 0. So what happens when I plug 0 in? That's going to give me a negative. So I know I'm going to be decreasing. And then finally, a number greater than square root of 7, I can use 3. It's going to be positive, so I know I'm going to be increasing. So tell me what's happening at negative square root 7. I kind of like to always do my little wave here. Think about what's happening graphically. I'm increasing. I get to negative square root of 7, and then I start to decrease. So I increase and decrease. So what's happening at negative square root 7? It's going to be a relative max. So I have a relative max at x equals negative square root 7. And again, my justification is f prime of negative square root 7 is equal to 0. And f prime changes from a positive to a negative. Make sure you're always able to justify. If you are using the first derivative test, you've got to state that the f prime of negative square root 7 is equal to 0. This is where students fall into a very ugly trap. Because then the next statement is where it falls apart, because you just simply say f prime changes sign. How come that is not a good justification when I'm talking about a relative max? Yeah, Ethan?
Because if it goes from negative to positive, you know it's kind of bottoming out, and therefore it's a relative min.
Exactly. So you got to be specific. When they're asking about justifications for maxes and mins, you can't just say change a sign. You've got to say it's changing from a positive to a negative. So then what's happening at square root of 7? Again, I'm going from a negative to a positive. So what's happening at positive square root of 7? Is it a relative max or relative min? relative min. So relative min at x equals square root 7. And again, you have to state for your justification, f prime of square root of 7 is equal to 0, and f prime changes from a negative to a positive. When you're doing justifications, you do not want to write a book. You do not want to write 3, 4, 5 sentences. You want to be concise, sweet, and to the point. You don't want to say too much because then you could end up contradicting yourselves and say a false statement. All right? So any questions on using the first derivative? I know your favorite, sketching. Like I mentioned, always pay attention to the graph that is given to you. Notice they are giving me the graph of f prime. This is not f, this is f prime. And we want to estimate the x values where we have a relative minima, relative maxima, inflection points. And then notice what they want us to do in part D. Give us a rough sketch of f. So we're going backwards. Given f prime, we want to sketch f. Well, first of all, let's figure out relative minima. Again, relative minimum occurs when what? F prime changes from a what? Negative to a positive. Remember, you read the graph of f prime just like you read a book. Where is f prime changing from a negative to a positive? 1. So again, right here, notice f prime is negative when it's below the x-axis. And then notice it's changing to a positive. So this is your relative minimum. Part B is asking about a relative max. Remember, this occurs when f prime changes from a positive to a negative. So where is f prime changing from a positive to a negative? It's changing where? At x equals 3. So notice, guys, when I'm giving you the graph of the first derivative, the relative max and relative min can be found at x-intercepts, as long as it's crossing over the x-axis. It can't just bounce off the x-axis. So when you're given the graph of f prime, relative mins and relative maxes you're looking at those x-intercepts where it's crossing. All right? So any questions when you're given f prime, how you can find the mins and the maxes? Now, inflection points. Remember, the inflection point is where f double prime changes sign, or where f prime changes from increasing to decreasing or decreasing to increasing. Remember, you're looking at the derivative of the derivative. So this is where you're looking at the slope of all your tangent lines. So notice, when I'm less than 2, all the slope of all these tangent lines are positive. But what happens with the slope of all my tangent lines when I pass through 2? They're changing from positive slopes to what? Negative. So where's my inflection point then going to be for f? My inflection point is going to be at x equals what? 2. So any questions on, given the graph of f prime, how I can recognize the maxes and the mins? So now before I construct my graph, let's think about the number line test I did for the first derivative. I know that my first derivative is equal to 0 at 1 and 3. Because now before I start constructing my graph, I want to look at the intervals where I'm increasing, decreasing, and the concavity. So let's take a look less than 1. Less than 1, the first derivative is negative, isn't it? So my first derivative is negative less than 1, so that what does that tell me about the graph of f? Am I going to be increasing or decreasing? Decreasing. From 1 to 3, what's happening with the f prime? Am I positive or negative? Positive. So what does that tell me about the graph of f? Am I increasing or decreasing? Increasing. And then greater than 3, first derivative is negative, so I am decreasing. Because before you start the construction of the graph, you want to know what intervals you're going to be increasing and decreasing. Now let's take a look at the concavity. Again, you told me we have an inflection point at 2. So when I'm less than 2, what can you tell me about the second derivative? The second derivative is what? Positive, so I'm going to have to be concave up. Greater than 2, the second derivative is negative, so I'm going to have to be concave down. Okay? Because you want to make sure you understand what you're doing before you start to do the construction. So any questions on this? All right, so now let's go ahead and start the construction. Everybody's going to graph these a little differently, which is fine, but there are going to be consistencies in a graph, and I highly recommend using a pencil because you may decide to move points around when you start doing concavity and increasing. First of all, I've got, I always like to find my inflection point. So my inflection point's at x equals 2. So what I like to do is kind of represent where I'm going to change concavity with this light dashed line. You don't have to, but that's where I know my concavity is going to change. And I know that if I'm less than 2, I'm concave up. Greater than 2, I'm concave down. So now I know that I've got a relative minimum at x equals 1. I have no idea what the y coordinate of f is going to be at x equals 1. So this is where the variations are going to occur in our graph. So I do know, however, I am going to have a relative minimum. So I'm going to put my point somewhere low on the graph. I know I have a relative maximum at x equals 3. So what I'm going to do is put a point somewhere at x equals 3, but I want to make sure it's higher than wherever I put the point at x equals 1. Remember, at x equals 1, this is where I'm changing, increasing, and decreasing. I need to be decreasing concave up until I get to that point at x equals 1. So I'm decreasing until I hit x equals 1. And remember, I need to be concave up. I'm going to change to increasing, still concave up until I get to 2. And I always show an inflection point kind of with a star. Let's change that. That's a pretty ugly U there. And now from 2 to 3, remember, I'm going to be increasing, but I'm going to be concave down. And then I need to be concave down, decreasing after I get to 3. This is where I always double check my conditions. Remember what I said from the number line. I have to be decreasing less than 1, which I am. I have to be increasing from 1 to 3, which I am. I have to be decreasing from 3 to infinity, which I am. I have to be concave up until I get to 2, and then I have to be concave down. Always double check your conditions. I have to have a relative min at x equals 1, a relative max at x equals 3.
So that whole thing could have been above the x-axis.
Absolutely. That's where the variation is going to be because, again, we don't know what the y values for 1, 3, and 2 are going to be. Any questions on that? All right, you guys go ahead and try B for me. See if you can find your relative maxes, relative mins, inflection points. Hopefully you came up with your relative minimum to be where? Where's your relative min? X equals what? X equals 1. Relative max should be where? X equals 5, and then you have 3 inflection points at -1, 0, and 3. So any questions on identifying the relative extrema or your inflection points? All right. Keep working on your sketches, and we'll take a look at them. But you get the point. All right, so again, there are going to be variations in our sketches, but again, as you can see, there's going to be consistencies as well. Like I said, if you're struggling, try doing increasing and decreasing first, and then adjust your concavity. Okay, try to do it in 2 parts if that helps you. All right, so any questions on section 4?